Here, I'll be constructing a comparator. The first thing we want to do is, for this first bit that we're comparing one to the other, we're going to use NOT and AND gates to compare the values. Now I've created the primitive comparator that we use to produce our overall 4-bit comparator. So as we can see, each of these AND gates is fed one of the values complemented and then one of the values uncomplemented. And it's opposite which value is complemented for each AND gate. So here it receives A complemented and normal B uncomplimented. So we can see that if they're both 0, we get an output of 0. But if A is bigger, then this bottom AND gate produces a high value. Similarly, if B is bigger, then the opposite AND gate produces a high value. If they're both the same, we also get a 0. And what we can do, since we get 0 for both, if they are both 1 or they're both 0, we can feed this into an exclusive NOR gate that will give us a high value if they're equal. So now we can compare, or we can tell if A is larger, we can tell if B is larger, and we can tell if they're equal. So we can use this to create our entire 4-bit comparator. So now I have the primitive circuits for each of our 3 bits, and we just need a good way to link them together and display the output in the way that we want. So here I put, this will be the final output if B is larger, and this will be the final output if A is larger. It's an OR, and one of the inputs I put into this 3-way OR is B2 greater than here, right out of this. Because I know that if the B bit is bigger than the A bit, if it's on the most significant bit, then B2, or just B, has to be larger than A. It doesn't matter what the other bits are if the most significant bit is larger. And that's the same for A. So if either of those are true, then the output will be true for that corresponding input. However, for these other ones, I'll have to know that B, or the first two, A2 and B2, the most significant bits, I want to make sure they are equal to each other if I'm going to output a high value for the second bit. So this AND gate here will serve the purpose of making sure that the most significant bit is equal, they're equal to each other, and then it'll make sure that this next bit is larger. So this will verify that B is bigger than A for the second bit, and that the most significant bit are equal to each other. Because if either one of those are bigger, then it doesn't matter what the second bit is. So this one, we could feed just right into B1 greater than. And we'll perform the same basic operation for the rest of the bits as well, making sure that the other bit, or the bits on top, the more significant ones. Now we have all our bits wired up, and the AND gates only produce high outputs if the more significant bits have outputted, if it's checked if the more significant bits are equal to, then it will produce the higher output. So if we check here, if B1, then we get a 1. If it's 1 0 0 0 or 1 0 0 versus 0 1 0, so 1 0 0 plus that, well, A comes out as the greater than, since the most significant bit is more. So that all works, but we still don't exactly have a way to test if they're equal to each other, other than knowing that both of these are 0. So we just take a 3-way AND gate and hook up all of our equality operators. Then we can have an option for equal to. And there we go. We have our full comparator. Here, I'll be making a 4-bit multiplier. So the way we're going to make it is, here is our first number, A. Here's our second number, B. And we're going to use ANDs for the multiplying, as well as 4-bit adders. Now the reason we have the adder as well as the multiplying here is because whenever we're multiplying numbers such that are 4 bits long, 4 digits, well, when we're essentially multiplying every digit in B by every digit in A. So we're going to take B0 and multiply it by A0, A1, A2, A3, and then add that to B1, multiply to all of it, B2, and then B3. So we're essentially adding 4 products, one for each of the separate digits. So now I've wired up our first 2 bits for multiplication and addition. B0 is being multiplied against every digit in A as well as B1. And then those 2 products are being added together to produce a sum. And one caveat here is that our B0 by the A3, this least significant bit, is being carried out. It's not being added. So it's going to go straight down to the output. And that kind of trend will carry on for each of these least significant outputs. And our product here, or not our product, our sum here, is actually going to be routed. Alright, and now here we have our final circuit for the multiplier. So I added all of the required AND gates to multiply each digit from B against each digit from A. And then each of the following products is then added on to those 3 most significant bits we got from the previous products. And the least significant bit of each one is dropped down. So these are the 3 that are dropped down. This is the sum of those final 2 products. And then that is the carryout bit. So if we have 2 times, say 4, and we get 8. We have 0 times 9. It's of course 0. And 7 times